the student, Brad Nelson, is here in the background doing important things like the video, but also he keeps track of the details about the seminar. So, has anyone here signed up to take the seminar? There were 2 last week. Oh, there you go. I'll send the book around. Anyway, I hope you know Brad here, just in case you have questions. Okay, well, I'm very glad to welcome Charles Martin back to talk to us. Was it a year ago, roughly?
About a year ago, yes.
Okay. If you were there, you'll remember a big scuffle trying to get this computer connected. But luckily, we're in good shape today. Charles did his PhD at the University of Chicago, right?
Yes.
In chemistry.
Theoretical chemistry, yes.
Okay. And then he studied physics.
Theoretical physics at Champaign-Urbana.
Yeah, and then he went to a place called the NCSA?
National Supercomputing Center, yes, NCSA. NCSA, so that was at Champaign-Urbana.
Oh, it's there.
So that's where we were. There was a fellow there at the institute.
Oh, okay. I was wondering where that was. Sounds like the NSA.
Yeah, not as good. Well, this is where Netscape was invented, so we got a little bit of credit for that.
Okay.
So.
Yeah. Well, Charles now has what, your own company?
Right. So we do consulting work in machine learning and AI, and
yeah. Oh, well, here's the name of the company.
so we just calculation consult. You do basic consulting work in the space. I've been working in this space for 20 years. It's really amazing how much it's come out. I did my postdoc work in statistical mechanics of neural networks and of vision science, things like this. So it's amazing all this stuff has come back because we were doing this in the 90s and it kind of died. And a few of us kept it alive, but it's just astounding. So today I'm going to talk about some joint work that this is me. So I've worked at a number of companies, BlackRock, Roche, Aardvark, which was acquired by Google. I've been doing this work in collaboration with my friend Michael Mahoney, who's at UC Berkeley. Yeah, you spent some time at UC Berkeley too, right? Am I allowed to say that at Stanford?
Yeah,
right.
A week of the same.
So Michael convinced me to do a little work in the field to try to understand why deep learning works. And we got to talking about this a few years ago at a conference. And here are some of the papers we've read. We have a number of papers we've submitted on this idea of what are called implicit self-regularization deep learning. And the slides will be online. We have a number of these, and a few more we've submitted this year. And I'm going to basically talk about first half of the talk will be some things I talked about last year, sort of where we are in the last. Second half will be all the new results from this year. The idea of this started by, sort of a few years ago, we started looking at what is regularization. There was a paper that came out, I don't know if you followed this paper, but now it's like 3 years old, right? ICME 2017, which was the best paper that year. People were trying to understand what is regularization in deep neural networks. And there was an example where they have a large model and they randomize, say, 10% of the labels. And they would find that at a certain point, you would always overtrain. You would always overtrain, and at a certain point, if you randomize too many labels, you always overtrain, and you can't fix it. Basic regularizers can't fix the problem. And there was a lot of hype about this back then, that this requires re-understanding what is regularization, what is generalization. And well, my take on this is known right as statistical physics. We know this from statistical physics. The idea is that when neural networks are overtrained, they're in speculized states, meaning that imagine you had the labels on a neural network and training some large data set, and you randomize n of the labels. So these little red lines, these are the ones that you randomized. This would give you 2 to the n solutions, 2 to the n possible solutions to the same problem. And you can imagine what this might look like in configuration space, or in weight space. You would have all these different solutions which basically look to generate the model. And you would overtrain them. And so what you would see is a system that would be, if you randomize too many labels, you get stuck in one of these solutions. And so locally you look convex, And globally, you're non-convex, and you're non-convex in the most pathological way you can imagine. You have an infinite, in the infinite limit, you have an infinite number of degenerate solutions, all of which are separated by infinite barriers. And so this is a very, very old idea. It's called spin glass. It's an old idea from statistical mechanics from the 80s and the 90s. And this was the traditional rethinking about how these models work. So we wrote a paper on this as, you know, rethinking generalization really requires remembering what generalization is. And I'll talk a little bit about some of what's in that paper later. But the basic idea is that we were trying to understand what is regularization. So the problem is in deep neural networks, every knob and switch is regularization. Everything you do. If you apply dropout, that's regularization. You change the load, you decrease the batch size, that's regularization. You add noise to the data, that's regularization. There's a paper I listed here, 50 different things, all of which are called regularization. So nobody really knows what's going on here. I mean, it's just a bunch of, and from an engineering perspective, that's fine. You're an engineer, you tune the knobs, you make it work. Okay. But from a theoretical perspective, we have no idea. Everything is called regularization. Please.
To me, regularization means that there is a solution and it's unique. But you're 50 ways old satisfied.
Right. Typically in regularization, you would have a set of degenerate solutions and you would apply a regularizer to find a unique one. You would try to find it. So a classic way of looking at regularization is ridge regression, or Tikhonov folds regularization. You know, something very simple. You give it a Russian name and it sounds very complicated, right? You take some linear equation, Wx equals y. You try to form the solution, which is the more Penrose-Sue inverse. Turns out this object X, it may not be invertible, it may be unstable for a variety of reasons, numerically or otherwise. So you add something to the diagonal to make it stable. Make sure you can invert it and you get a solution. And this gives rise to a familiar L2 optimization problem. So this is traditionally what we think of as regularization. You soften the rank of the matrix. You try to focus on eigenvalues that are larger than some scale. And the typical way of looking at regularization.
This could be X.
Did I make a mistake? Yeah, I may have made a mistake. I'll fix that. Thank you. The idea then is that let's suppose we want to do the same thing for a neural network. The neural network function, once you train it, consists of weights, some weight matrices, maybe some biases. So we write down an energy function. And the energy function is a bunch of weights for each layer convolved into some activation function, like a sigmoid or a ReLU. And they're sort of stacked inside each other. And then there's some biases. You have basically a function which is a function of the weights and biases. Those are the adjustable parameters. So we think of the weight, basically a weight space. And then you minimize the loss of this object by taking some data, putting the data in, assigning labels, and you take whatever the predictions are of the neural network on the data minus the label, and there's some loss function, like an L2 loss or a cross entropy or something like that. And that's typically what you do. And so we set the problem up like this. What's interesting is that the energy landscape only depends on these weight matrices and the biases. That's what defines it. So other things like adjusting the batch size, what does that have to do with the optimization problem? You know, normally you would think I have an optimization problem and I solve it. And in neural networks, what happens is when you change the features of the solver, you actually do completely different problems. So we're trying to distinguish between these two. So what we would do here, what we find is that, let's suppose we do spectral analysis of the weight matrix. We want to analyze the regularization of the weight matrix in the same way you look at Tikhonov regularization. You look at the eigenvalues of some matrix A. This shows you W, the weight matrix. But we form some correlation matrix over these to be the weight matrices. And we look at the eigenvalue density. In other words, we form a histogram. And typically the singular values square the eigenvalues. And so by looking at the eigenvalues of the weight matrices, we have this idea that we can learn something about how the regularization is performing in the neural network. And so that's what this talk is going to be about. It's going to be about looking at this density of eigenvalues in real systems. So in some sense, I'm just a theoretical chemist, right? So what do chemists do? You have a molecule, you shine a light on it, you look at the spectrum, right? So you do spectral analysis of molecules and you form a quantum theory around it. Same thing we're doing here. We're going to do kind of like spectroscopy on neural networks, and what do we find? Well, we start off with something very small, like a simple multi-layer perceptron, 3-layer multi-layer perceptron, and we do spectral analysis. This is the singular values, and these are the eigenvalues. And in this case, the weight matrices in this model are square. So in the case, this is the aspect ratio, Q equals 1, so N over M, so the shape of the matrix. So it's sometimes useful to look at the singular values. What you find is that there's a bulk region of singular values, and there are these little spikes that pull out. And these little spikes contain, presumably, all the information that the neural network has learned. And if you look at the eigenvalue spectrum, you see the same thing. You sort of see this bulk region, which is in sort of purple, and then these spikes that come out here. And we realize very quickly, okay, that's interesting. If you just look at a random matrix, which is the random matrix will not have the spikes. So the random matrix will either be the semicircle or this sort of crisp, this density. And so what we're doing here is actually very simple, right? This is not a complicated thing. This is the Python code. We just get, imagine you have, in this case, Keras. You just go to the model, get your layer, get the weight matrix, compute the shape, get the dot product of the eigenvalues, normalize, compute the eigenvalues, and make a histogram. That's all we're doing. We actually use SVD. So we brought this up last year to do this. But this is just to show you this is like 10 lines of code. It's not particularly complicated to do. Now, what's interesting is you get a breakdown of as you train these systems more and more, you get some very interesting behavior. So this is an example of where I took a neural network, a very small one, and I systematically decreased the batch size. Now there's this very strange phenomenon that occurs in neural networks. It's called the generalization gap phenomenon. And it's this funny thing that when you change if you shrink the batch size of your solver, you get much better results. Holding everything else constant, just change the batch size, make it smaller, and you get better results. No one has any idea why this is.
Define better.
It generalizes better. You're better if you generalize better on an unknown test set. So I did an interesting experiment where we start off with batch size 500, which is very large. And typically people use large batch sizes because they want to get all the memory and the GPU used. And if you start off with a large batch size, you see what is essentially a random-like structure. And this red line is it's called random matrix series, Marcenko Pastur random matrix, so you get almost perfect fit. And then as you decrease the batch size, you start seeing this little shelf appear of spikes. So so you get this shelf of spikes with some of the information, and it sort of separates off from the bulk. And there's a good separation here. If you know anything about random matrix theory, the separation is much larger than, say, the traceability fluctuations you would expect near the edge. At some point, though, the edge breaks down. You get this sort of bulk decay. And pretty soon, you go from having bulk plus spikes to what is essentially a heavy-tailed matrix. So a much better model, rather than use random matrix theory, where you get these sort of really poor fits, is to just fit this to a power law. And this seems to work very, very well. And this is sort of when we first began to realize that we have this conjecture that when you train a neural network, that the training process of backprop using SGD somehow induces a type of heavy-tailed self-regularization. And this is what the talk is about, is really probing deeper into what that means and what you can do with it. So we started off with this. And this is just, if anyone doesn't know random matrix theory, the basic idea of random matrix theory is that if you give me a matrix and you select the elements randomly, like from some Gaussian distribution, and you go to the infinite limit, I can tell you what the eigenvalue spectrum looks like. So I can tell you what these densities should look like. And depending on the shape, N over M, you get a structure that has a very simple shape, well known, it's analytic. It's a very crisp cutoff. So it's a very crisp cutoff of this bulk region. And we know exactly what the fluctuations look like at the edge. So you can sort of trace the fluctuations at the edge. And the eigenvalues are tightly bounded. So the eigenvalues, depending on Q, you know exactly where you should be. So this is called Marcenko Pastur random matrix. And it turns out that there's a variant of this, which was developed in the theoretical physics literature, not as rigorously as some of the Marcenko Pastur work, but the idea is that we know that if, for example, you were to draw the elements of the weight matrix from a heavy tail distribution rather than a Gaussian distribution, then the eigenvalues would be dominated by the largest element of W. So you would get a heavy tail distribution. So what the physicists do is they sort of go backwards. They say, well, if we have a density and the density looks like it's power law, it can be fit to a power law, then we're fitting really the correlations. And so there's this notion in physics that when you see power law in your correlations, something special is going on. And some work showing that this is really like having a completely different universality class for random matrix theory. In other words, all the theorems of random matrix theory break down because the system just shouldn't behave like this. Your system is too strongly correlated. It's not random. And that's, of course, the point. When you train a neural network and you look at data, you're trying to learn the correlations. You would not expect the weight matrices to be random. You would expect them to be strongly correlated. So this gives us a way of, I think these pictures, by the way, are out of, this ideas come actually from finance. I used to work at BlackRock as a quant, predicting markets. And these are theories that were developed for denoising the covariance matrix of the stock market. So a lot of work comes from computational finance. A lot of the stuff we're doing, a lot of the theoretical work is developed by quants in finance. So what we did is we started off, we wrote some of our early work, is we just wrote down phenomenology. Let's, so basically we wrote a tool, that tool is called weightwatcher. Hit install weightwatcher, and it will automatically do these fits for you on every layer of your weight matrix. You give it some pre-trained model like BGG or ResNet, it will do it. And it will identify what region you're in. And so we sort of made these regions that are random-like, or bleeding out, so the edges are bleeding out, or you can see these spikes, bulk plus spikes, which is a very specific model of statistics, or then you get this sort of bulk decay, where the edge is sort of, the edge is gone, and then you have heavy tail, very different version of heavy tail, depending on how good of a power law fit you have, and then you have singularities, where you have just complete rank collapse. In other words, antibodies go to 0. And we call this the 5+1 phases of training, and we have a very long, like 50, 60 page paper where we go into great detail about all this kind of stuff. And in specific, we talk about identify these different universality classes in the literature, mostly in the physics literature, and talk about what the elements look like that you would expect that would generate these universality classes, and sort of what the global shape of the ESD would like, what the tail statistics look like. And the idea is that each of these universality classes corresponds in sort of qualitatively to one of these qualitative pictures. And then that's the idea, other than the rank collapse, which is just, well, that's actually all that too, because you lose rank. So we sort of put around this sort of phenomenological theory. That's where we started. And we're much farther ahead now than this. Now we're at a point where we actually have a full statistical mechanics theory of what's going on. And I'll talk, when I get to the end, I'll try to talk about that. But the paper is very technical. We go through great technical detail about all these things. But primarily the idea is that what you care about is what the shape is, how far the spikes are out, and what happens here at the edge. I mean, do you have a nice crisp region, or do you have this sort of change in convexity where it really looks powerful? And what I want to do now is show you some real examples of this. So when we sort of put this theory together based on random matrix theory, some people like it, some people push back and go, I don't like it. That's okay. It's a phenomenology. Okay. Now what we want to do is we spend a lot of time looking at pre-trained neural networks. Now when we started this work, there were maybe 50. So what happens is people train these neural networks like Google, and then they give them to you, and you go do terrible things. I have clients that do some naughty things with them. And, but the point is that we started with maybe like 20 or 30 of these, maybe 50. Now there are hundreds of them. Hundreds of pre-trained models. I think just for NLP alone, the BERT model, if you guys are going to see now again, the BERT model for NLP, there are over 100 variations of the BERT model for all the different languages, uppercase, lower. So there are hundreds of, we want to start looking at pre-trained neural networks. Remember I told you I used to be a chemist. So this is like doing spectroscopy. We're going to look at these things. And it's sort of, we don't know anything about them. We don't know how they were trained. I don't have access to the data. Mahoney doesn't know how to, we can't figure out how to give you the data. So we couldn't figure out how to give you the data. Just don't give me the data, I'll just look in the networks directly. So I never even look at the test data. I don't have the test data or the training data. So imagine like you're in a company and someone gives you a model. They're like, here, put this in production. How do you train it? Don't worry about that. Who trained it? Don't worry about it. That's how it is, right? Someone gives you something, and that's what you think is going to happen, right? You just get these things. And so we start off by looking first at some of the early convolutional models. LenNet 5, which I retrained. AlexNet, Inception, ResNet, DNNs, and so on. So we have examples of all of these. And we want to look across different kinds of architectures. And I'm going to show you, for example, what is the traditional computer vision architecture was convolutional net pooling, fully connected layer. So these original models, back when I was a grad student, postdoc really, these were based on trying to models with the primary visual system. And then later people said, well, yeah, these things don't work, so why don't we try to optimize them? So they created things like ResNet and DNNs, where they added residual connections and tried to shrink the layers so they could all fit into memory and put them in hardware. So we began to look at these. And we find something very interesting. If you look at the old models, small models, simple models, toy models, they look like this. They look like Marcenko Pastur theory, really good fit to the bulk, plus some spikes. And if you do something like compute the soft rank of this model or some measure of the soft rank, you might find it like 10%. But they all sort of convolutional maximal, this very, very small model. This is the stuff that I used to use back, in the 90s. Every other model we look at, every other model, AlexNet, DNN, ResNet, Inception, BERT, OpenAI, GPT, they all display in one form or another some sort of heavy-tail behavior. They all can be fit pretty well to a power law. The Marcenko Pastur fits aren't very good. You can do them. We've automated all of this. You can do. But we really think a better model is either bulk decay or heavy tail. So this, for example, is AlexNet, and we're just looking at the first couple fully connected layers in AlexNet. And you can do it yourself. There's this funny thing that people say that deep learning research isn't reproducible. It's very strange to me. It's not a computer. You have the data. So we wrote a tool. I have a bunch of notebooks. You can run them yourself and verify. 100% reproducible. So we see this in a wide variety of models. Go ahead.
So you said something like a better model is bulk decay. So what you presented earlier was you showed 6 panels, and they have evocative names, but I don't understand how it's a model. I understand that it's a phenomenological description, and it does seem persuasive to me, but how do I say I have a bulk decay model that fits the data?
Okay, so 2 things. One is that we have this method that we use to actually try to do power law fits, and that's always a little controversial. But we use it. But there's basically you do a power law fit and you measure some other types of models and you compare something like a KS distance between them, and you say, well, it looks like the power law fit or truncated power law is a better fit than some of the other models we have.
So okay. Well, if I understood what you just said, then you're saying that would seem like a way to do the heavy tail case, but I don't see how it's a way to do the bulk decay case.
I agree. The bulk decay case, this is really phenomenological. We put this together because we were trying really to provide some guidance to people who aren't quantitative. And they can sort of look pictorial at it. So the idea of the bulk decay is that, well, maybe the power law expert is kind of high. So the idea is that you have this sort of power laws between 2 and 4. You might get an expert between 2 and 4. And between 2 and up to 4, you think you're pretty heavy-tailed. And then when you're higher than 4, maybe you're up 5 or 6, we sort of call it moderately heavy-tail or bulk decay. It's not, and the reason being that there are these, depending on what the power law expert is, you see really very qualitatively different behavior in the spectral density. So I wouldn't take it too literally.
But it is really interesting the actual network you were showing. I forget what it was.
I'll give you an example. What is that? Is that bulk Or is that heavy tail? We're not sure, right? That's just sort of, the mass isn't filled in. So we have sort of funny things like this.
So at this point, you don't have like a formula for bulk decay with parameters that adjust to fit the data. You have.
I have
a diagnostic.
I have a theory based on statistical mechanics, which I'll present about. I'll go through that. It's sort of the idea is it's more phenomenological. The idea is you look at these models and you measure. You try to measure their. Well, here's an example. Like you would measure the exponents. You look at all the layers and you measure all the exponents. So here's an example of these are ImageNet models. So we took a bunch of PyTorch models out. We fit them all with this power law method. And the power law method we use is it's this MLE method. It's not that great actually. Once you get like a past 4 or 5, I'm not sure I actually trust the value of the exponents because it's not really a good fit.
But it's some sort of truncated power law.
Some sort of truncated power law with or without the mass. So
that's enough for me.
Got it. Okay. So in fact, that's exactly what we've been doing. We've been looking at so sort of the qualitative idea here is that jump off a little. In these bulk decay systems, in the bulk plus spikes, there's a standard model for this. And the idea is that this is kind of like traditional regularization. There's a cutoff. All the eigenvalues that are larger than this sort of bulk edge, these are the ones that carry most of the information. Then you basically kind of ignore these eigenvalues, although you're not really like ignoring them totally, you just sort of soften them. So there's this notion that when you're in these older models and you see this kind of behavior, this is like a type of Tikhonov regularization. It's very similar because there is this scale cutoff. And what we think happens in the other models, when you really have this power law behavior, really what we're saying is that you need to keep every single eigenvalue. You can't throw any of them away. If you throw any of them away, you're gonna lose something fundamental about the model. You're not gonna be able to generalize it. And so there are people who want to do things like they want to take the weight matrix and do like a low rank approximation to it. And what we think is that once you start getting power law exponents and the exponents are due 2, probably those low rank approximations aren't going to work very well. You probably need to keep everything. And that's sort of the idea here. And the idea it's that every single eigenvalue matters. To really, you can't really throw anything away. And so what we're going to do is we're going to show you some experiments on, we looked at tens of thousands of these now. In fact, I think the last time we did it, I had an intern, very nice, Serena Ping from UCLA, finance, very great intern, better than a lot of the, I don't know, she's fantastic. And we've studied hundreds of these models now. They all have this sort of characteristic behavior. If you look at the PyTorch, the computer vision models, you see a lot of the exponents start to concentrate near 2, which is sort of the bottom of this universality class. And then maybe you have some outliers out here. These are probably like bulk decay because the exponent's it's not below 4, but it's not too large. When you go to the natural language processing models, we see qualitatively different behavior. The exponents are usually a little larger, but they're still between 2 and 4, and you see more outliers. And so we did this a couple of years ago. This was on PyTorch and Allen NLP. And then we will sort of plot them all. Like you plot thousands of them. You know, this is I think 500 matrices over 50 architectures. Excuse me, 75. It should be 7,500 matrices, not 500. You see this sort of, they all concentrate around 2. And you know, if you're a physicist, well, it's sort of like this notion that generally speaking, we expect that really well-trained models all have exponents of around 2. And that's sort of the conjecture, that we think this is sort of the limit of where you're going to be. And that if you have a really good model, and you train it really well, and you have enough data for the model, that the exponents will concentrate around 2. And it's very qualitative, but we're going to show why this is the case. Go ahead.
So there's some sort of international standard for data, because singular values don't mean much unless you know you've normalized every column or done something to scale the data.
of the scale. So you want to talk about the scale?
Well, do you normalize the columns, for example?
No, we don't actually. The only thing I do in the scale, because we don't. What happens when you train these neural networks? You get a weight matrix, and if you look at how they're normalized, they usually start off. If you go inside the initialization, they're usually initialized to something like 1 over square root n, or something similar to that for the convolutional maps that we're looking at. And so the only thing I do is rescale the convolutional map. I think it's by k over square root 2 or square root 2 over k over square root 2 to just kind of resize them. Go ahead.
So a lot of standard models are based on batch normalization.
Yes.
And so for batch normalization, the weight matrix is operating on a normalized entity that has mean 0, standard deviation 1. So that induces a quasi-normalization?
Yes, it does. So what we found, and I thought about this a lot, is we're trying to build a practical tool. And so there are some metrics like alpha, which are basically scale invariant. They're not going to depend on normalization. You fit the alpha. But we're going to introduce these other norms, like the Frobenius norm, the spectral norm. They will matter. So the alpha is basically scale invariant. It doesn't really matter what scale you fit it at. But some of the other metrics we're going to introduce are scale invariant. And what we found is that, and I looked at this very carefully, at least looking at all the hundreds of models I've seen, for the most part, you don't have to normalize. Like normally when you write down this equation, normally you would normalize this by 1 over n, if these are weight matrices. But we don't do that in a neural network. We use the normalization that's built in because they seem to already be normalized. And if you change the scale, you just get very strange results.
But then there's nothing to do with the numbers in A. They could be anything.
The numbers in, well, they're just what we get out. You know, we get a weight matrix and we look at it.
But I mean, you said X is A transpose A. If you scale the numbers in A in any way.
No.
So
no.
Mike, roughly speaking, the A that he's talking about, view it as it's the product of complicated optimization. And in that optimization, A is always acting on a specially normalized entity. And so the kinds of A's you're going to get out of the optimization have a kind of conserved scaling. Okay, let's say that's a heuristic.
Yes.
It's a theorem.
Well, no, theorems are hard to come by in this. What I would say is we studied, for example, what the Frobenius norm looked like, and we've studied how the spectral norm behaves, and we've studied various scale-dependent metrics, and I'm going to show you some of those. You'll see, maybe that'll help.
Well, it's not just any old A. You have to tell us where A is coming.
It's the weight matrix of the neural network. We just pull it right out of the model. It's the solution to the neural network that they found. Okay, so last time I was here, I made this conjecture that this is the original BERT. And if you look at the power law exponents, you get a bunch of them that are sort of between 2 and 4, maybe 5. You know, our estimator, this is probably pretty good for the estimator we're using. And then these things out here, maybe bulk decay or bulk plus spikes or some other horrible. They're really outliers. And if you dig into them, sometimes they just look like sort of they're not well correlated. And I had this conjecture that someone's eventually going to fix this up. And so we started looking again, and we find if you start looking at some of the optimized BERTs. So this is an example called robust BERT. And in robust BERT, I compare robust BERT to BERT, you find that a lot of these outliers go away. There's still a few of them. But curiously, the alpha sort of moves, the peak moves a little bit to the right. But you lose a lot of the outliers. And so we sort of conjectured that as models are better trained, you should really see the power law exponents concentrate down here in this between 2 and 5, maybe 6. And you shouldn't see these outliers. These outliers are exhibits of, they're probably, to me what I say is that the model's not trained well enough. You don't have enough data or the model's over parameterized. Yes?
You
said that the MLE estimation procedure that you use for
power law estimate, yeah.
You don't trust it past which number?
It's good like between 1.5 and 5.
Okay, is it possible that this change may just be an artifact of different kind of set of matrices, or do you know that this change is, actually?
The change meaning BERT?
Yeah, like
no, you can go and look at the weight matrix, and they don't look. And you can actually go in and inspect them, and they look more powerful. There's more powerful looking weight matrices.
Okay, so this change between the two BERT models could not be an artifact.
No, these aren't artifacts. I don't think it's an artifact. It's a good question. Yeah, we have the tool we wrote. You can plot all of them. I can go to law. And here's another example of distilled. And distilled, you see the same thing. You don't see these outliers. Sometimes when you go and look at the outliers, you can see spikes, or they're not well fit. But it's a good question. We're not that happy with the estimator. So I'm sort of using it now as an engineering tool, and I'm kind of closing my eye and I'm ignoring the fact that it's out here. It's not really. It's just sort of like a trend that I'm hoping is good, right? But we see this behavior. And if you do it for OpenAI, you guys know about OpenAI and GPT? So this is this model that generates fake text. So I have a client who's generating fake text now. They sent me an email like, oh yeah, 22 paying customers. So we helped them do this. So it's amazing. So GPT was the first model that was released, and this is this model, and it was like, go to this OpenAI guys, we're going to release this model, and it generates fake text, but we're going to purposefully train it so that it's bad, so that text it generates isn't very good, because we don't want people to misuse it. And so that day I got a call from my client, can you help us fine tune this? And so, we got to look at the weight matrices, and we start doing this. Then, I don't know, a year later or so, they finally admitted, we're just going to release GPT-2. And so this is an example of the exact same architecture, but the red represents the later trained on a much larger data set using a better training technique. And again, you see that this case even more. The alpha is the average alpha, and here, all these outliers go away. Like there's no more outliers. Maybe these color. And you see the alpha moves down smaller. So this is a really good example of, to me, is this example where you have a model and it has a bad, what's probably the hardest problem you have in industry? Is your data any good? Right? Everyone can train a model. I have a friend who works a PM at one of the self-driving car companies. They spend like $5 to $12 per labeled data point. And it's millions. So the question is the data any good? And so the point is that what we try to do is ask, you look at your model trained on your data, and basically, bad, good. We're trying to give you a metric that can tell you something's wrong. There's something wrong. Even if your test accuracy looks good, there's something wrong here. Your alpha shouldn't be that large. And that's our conjecture. It's a conjecture that you're not correlated enough. Something's wrong. So, here's some examples of what I call correlation flow. So these are examples of the alpha as you go down the layers. So we can make plots down the layer. I'm going to give 3 examples, VGG, ResNet, and DenseNet. So if you guys don't know anything about computer vision, VGG is sort of the original model that was released. Then the link, and it's sort of like not very well optimized. It works, but it's really hard to train. It has a huge number of parameters. It takes a lot of memory. And then people came up with ResNet. And ResNet has these called residual connections, which allow you to have, presumably, you don't get, the gradients are better behaved. So we find interesting, in VGG, the alpha, here the blue is the worst, VGG 11, and the orange is VGG 19. So the 19 is the larger model. So, and 19 is more accurate. And what we find is as you go down ResNet, the alphas get larger. And then these last, they're kind of small for the last 3. These are the last 3 are the 3 fully connected layers, which are much smaller. So they sort of go up like this, and then the last fully connected layers concentrate the correlation. If you look at ResNet, you see very different behavior. ResNet is so good. People have trained ResNet to up to 1,000 layers. And so here is this interesting behavior. If you look at this is ResNet 18, the smallest one you can have, the alpha is sort of there. The larger one, the alphas are all correlated. They're sort of mostly around 2 until you get to the end, and then it kind of goes a little bananas. So this is mostly really good power law behavior, good fits. And then out here, who knows? DNNs is interesting. DNNs said, well, we've got ResNet. Let's put residual connections everywhere. Let's connect everything to everything and see what happens. And here the alphas are kind of around 2. Look at the red. Look at the red because that's DNNs 161. But there's all this other stuff up here, and it's kind of saying to me, well, the story is sort of a story after the fact that it looks like VGD doesn't have any residual connection, so it doesn't flow well. DNN has way too many. So it's like, you know, when you go home, people are driving. I live in San Francisco, and people get on Waze, and they drive all over, and they go on like the 50, you know, my street is 50 miles an hour. They still try to, you know, I'm always, there's people with dogs, you know, and it's sort of like, ResNet has way too many connections, and ResNet seems to be about just right in terms of what the flow looks like. So we've been studying this idea we call it correlation flow, and looking across, and so we're trying to give an engineering view as a tool to say something about how your architectures perform.
So would that say that the ResNet starts to have too many layers when the alpha gets big like that?
No. In fact, what happens is, I'm not sure. One of the funny things that happens is near the beginning and the edges of the networks, you get funny behavior. So we've seen, for example, the Frobenius norm sometimes is large at the edges and then flattens out in the middle.
That's an awfully wide edge, though. That's 100 or 50 or something. Like,
yeah, it sounds like 400 layers.
So still, the edge I can imagine the last 1 or 2. The 50 seems like
it's, you know, it's hard to say, right? I'm still a chemist right now. Now, one of the things is we have different measures of rank, and one of the things you can think about qualitatively, what is alpha? Alpha is kind of like a soft rank. So if you were to measure the Frobenius norm relative to the maximum eigenvalue, and that's basically what alpha is. If you take a heavy tilt matrix where the alphas are smaller than 2, like between 1 and 2, and you plot the log of the Frobenius norm versus alpha log of the max in a very nice straight line, and then we get sort of above 2. It's kind of straight up here, but it can miss. If this is the finite size, this is for matrices that are very, very large, like M is 10,000. For the matrix sizes inside deep learning, we sort of see this sort of finite size behavior. So, and so you think of alpha as a soft rank, a version of stable rank. But it's not exactly the same, but it's like a stable rank. And this, and we also, by the way, we have another metric I invented. I had my own metric, which I call the MB soft rank. So in cases where you're very heavy tail, alpha is a good fit. If you're up here and you think you have a bad fit for alpha, I have another metric I invented. We just take the maximum eigenvalue divided by the bulk edge. And the tool we wrote will automatically compute this for you. So we actually can compute, I just call this the MB soft rank. So it's just another scale invariant measure which would allow you to get a metric of what's going on when alpha is a really bad fit. So I just sort of made this up and we have in our paper, and this is what it does. Turns out it's not bad. So one of the things we try to think, okay, the fact that the interesting thing, we say that when you have better models, alpha gets smaller. Now what can we do with this? Theoretically, now we get some of the theory part. Well, maybe I can predict the generalization accuracy. So there's this idea that there's these different theories people try to predict the generalization accuracies. But they never actually do it on real, like apply it to real systems. Maybe they adjust some of the hyperparameters. But I said, what if we actually try to predict the generalization accuracy of a model? Well, let's see what would happen if we just run some correlation tests. So one of the things I use, alpha, I take a weighted alpha. So I'm not going to look at alpha, but I'm going to look at an average alpha, a weighted average of all the alphas. And the weighted average, the weight should be something like the scale of the matrix. Because larger matrices should contribute more than smaller. And so what I sort of invented is an unsupervised VC-like data-dependent complexity metric, which can predict or at least show correlations in the trends in the average case generalization. I'm a physicist, we do average case, we don't do balance, we do average case. So this turns out to work really well, amazingly well. So I want you to think of what we're going to do. Is we're going to take a product norm. Imagine we take some norm on the weight matrix of our neuron. And we're just going to assume that every layer is statistically independent. Why? Because I need to do something that I can do. So, now maybe not a good approximation, but I can do it. So I'm just going to do that for now. I would take log, and I take the log of the product, I get a sum of, I get a log. Log of a product is the sum of the logs, and so I get sort of an average log. So I'm going to say that the average log of some norm on the weight matrix is a complexity metric. It's a product norm. It's like a data-dependent capacity. Forgive me, sometimes that makes up capacity and complexity. So basically, it's a measure of the complexity of. It's going to try to give you a trend in the generalization accuracy. And then I ask, can we measure a trend? Well, it turns out, if you use a Frobenius norm, it's not bad. Frobenius norm actually is somewhat correlated with, if we look at a series of models like VGG, this is with without batch norm, I don't have the label probably, but it's actually not bad. As the norm gets smaller, the test accuracy gets larger. It's not bad, it actually correlates. There's no reason a priori this should correlate. I mean, this is the Frobenius norm is a regularizer, but there's no reason why it should work across different architectures. But it seems to. So I just said, what if can I actually do this? So I'm going to use this term before, this log, alpha times log lambda max, which is sort of this metric where an average alpha, what alpha hat, where the weight is the log of the maximum value. So remember what we're doing. We're fitting our ESDs to a truncated power law. So 2 parameters. Power law exponent, max the cutoff, maximum value. So those are 2 parameters we're going to use to define our complexity metric. I'm just going to take for any linear layer, I'm just going to take this. For the convolutional layers, I'm going to do something kind of funny. The convolutional layer is usually k by n by m. And I'm going to take k squared n by m slices. And I'm going to rescale them up by like k over square root 2. Because if you check the normalization, that's the right way to scale. If you go inside the code and look. So this is not necessarily the right way to do convolutional layers. The do SVD of a convolutional layer, we can talk about that. I have other code that will do that, but this is a very simple, crude thing. All right, now I'm going to measure. I'm going to measure now. I'm going to take all the VGG models. I'm going to plot the test accuracy versus the metric, these metrics. So these are VGG 11 to 19. And I take these right out of Tikhonov. So this is totally, and you find that Frobenius norm, as the average log Frobenius norm gets smaller, accuracy gets better. RSE 5.6. Okay? Spectral norm, largest eigenvalue, up to some scale. Same thing, RSE 0.53. Alpha hat, RSE 0.48. So they all work pretty well. It turns out that the test accuracy is actually pretty well correlated with these metrics. They all perform pretty well empirically. We're the first ones I think ever point this out. Yes?
So there's a theory paper, guy in CS at Berkeley that says that in the mid-90s, and he said, Peter Bartlett.
Bartlett, yeah.
But what matters is the size of the weights for neural net test accuracy. So it has a theoretical argument.
It could be, yeah. He's been in forever. You know, he was in the field when I got in. I left, came back, he's still in. So he could be right. Yeah, the size.
Well, is that not what you're showing?
Kind of. I mean, I'm measuring the spectral density. The size is really here, the Frobenius norm. That would be the size. So what I'm going to argue is I can do a little better than that. I'm going to make an argument that I do a little bit better, usually by using these alphas, by adjusting for this. I'm going to make an adjustment to that by correcting for this power law exponent. I don't actually know exactly what he does. It's possible that he's doing something better or similar.
Well, it was 25 years ago.
I probably should have known it back then, but
so there's some precedent for what you're showing.
No, it could be.
I actually never saw anybody show me data confirming this.
No, nobody looks at data. We try to submit. Okay, why are you doing experiments? They go, I don't know. This is what an engineer should do, right? I mean, it just seemed like the right thing. I mean, in physics, we give you experiments. No one's ever done data. It turns out these alpha And other cases like the stable rank and the soft rank can actually sometimes be anti-correlated. And when we're anti-correlated, we're actually the worst. We're going to be anti-correlated with us. So, and that's because remember before I was showing you that the correlation flow of the alphas get larger? Because the alphas are getting larger, the average alpha tends to get larger with the test accuracy. But what we want is things to get smaller. And so we don't really use, so it turns out things like the stable rank and the alpha, the average, those aren't good metrics because they don't account for the fact that these things are changing. You really have to account, you said, for the size, the weight, the size is what matters. So what I do is I have this statistical mechanics argument. I might call it a theory as much as an argument. But what I'm going to argue is that the right thing to look at is log the Shackman norm to the alpha. So I call it alpha alpha because typically people take basically I'm going to look at the sum of the eigenvalues all raised to the alpha power. And I'm going to take that sum. So think of it like this. And I'm going to take the log of that. And alpha log max is approximately equal to this value. So what I'm going to argue is that the way to measure the scale would be to take the eigenvalues, fit them to a power law, and then raise them to and then take the sum of that, the sum of all those eigenvalues, and raise them to the alpha power. And that's going to be basically what this thing is. And it turns out that, here's another example. I do VGG. If we fit with the empirical fit, we get 0.48 RMSE. If we use this sort of, I call it the alpha norm, which is the Shack norm, I get RMSE 0.34. I get it a little bit better. It turns out I can do this for ResNet. I can do it for DenseNet. I can do it for ResNet 1K. And if you compare across different models, I do the same procedure. And VGG has 6 models or 5 models. The ResNet 1K is the same architecture but trained on more architecture trained on a smaller data set. And if you look at the RMSE, generally the alpha log max, so these two are basically, this should be log, I should say, but basically these two things are basically very similar. So you might see here for ResNet, you would get 0.9, 1.4, where on my approach it's 0.61 or 0.66. Or if you look at ResNet 1K, the RMSE is 2.4 for Freenis norm, 3.6 for Spectral norm, weighted alpha is 1.8, alpha norm 1.9. So I'm going to make this empirical argument. In fact, I had a nice intern, Serena, work with me. We looked at over 100 of these. So we systematically looked at all of them. And we looked at 100 pre-trained models. In fact, what we did is we looked at 500 pre-trained models. And we looked at these different series of architectures. But we only selected out ones where there were at least 5 points on the line and you correlated properly. I mean, I wanted these 5 points. So there's a joke in physics. You know, we say 3 points makes a straight line in physics. In chemistry, 2 points makes a straight line. In biology, 1 point makes a straight line. And in economics, there's just a line. So I wanted these 5 points. And so we systematically did this. And this is all, so I looked at this, I think he's a Russian guy, who has gone and bothered to retrain hundreds of models. So there are hundreds of these models now. So we looked at about 100 of them, roughly 100 of them, across these 5 different data sets, and ran these regressions. And again, what we find is that the R squared is about the same. Maybe the spectral norm is a little better than ours, factor R squared. And for the RMSE, we're much, much better. We're much, much better than Freenis norm or spectral norm. So this is sort of the empirical argument. And this is sort of the kind of things we're doing. We're trying to make this tool that you can do spectral analysis of weight matrices of pre-trained models. I have a tool, it's in Python. This is how you run it, it's very simple. So my argument is that everything should be 100% reproducible. This idea that things are not reproducible to me is just, bananas. So the tool is reproducible. We have a Slack channel, we're going to go on the Slack channel and try to use it and try to maintain it. All the experiments we've done are written in Go. These are all in a repo in a repo on the package, which you can run on Google Colab. So you can run them all yourself for free. You have to run anything to run them. There are 5 different notebooks. It takes 50 hours or so to run all these experiments on Google Colab, all free, 100% reproducible. And if I did something nutty, then let me know. So this is what we're doing in terms of trying to understand how to use alpha. So can I use alpha as a complexity measure? Now that I did all this, So, well, now I need a theory. So I have this is the last part of the talk, and you can, I'm just running out of time, but basically I worked out a statistical mechanics theory for where this comes from. And the idea of this, I don't know, has anyone here done statistical physics or theoretical physics? Okay, I got some. So you're probably better at this than me. I had to dig all this out. But the idea is I'm going to make I'm going to take a student-teacher model, which is a classic model for neural networks. And I'm going to make a matrix generalization. And what I'm going to do is I'm going to use something called random matrix integrals, or HCIZ. It's Dixon's, I can never pronounce it correctly. It's Dixon super integrals from quantum field theory. I'm going to just basically use some results from random matrix theory to derive the generalization error. And the idea works something like this. In the standard student-teacher model, you have a perceptron. And in a perceptron, you have these weight matrices, but just treat them as vectors, and they're random, and they're Gaussian. And you just imagine I have a teacher, and the teacher has some weight matrix that you learned from the optimization problem. And you have a student. And the idea of what does it mean to generalize is that, given the teacher model, how many students are there that can reproduce the results of the teacher exactly? And then you do something like you integrate over all possible random students for all possible random teachers, and you compute the error. And so this is a classic problem that comes out of Engel and Vanderbroek in the late 90s, 2001. And so the idea is if I know this overlap between the student and the teacher, I can compute the generalization error, which is related to the phase space volume, where the phase space volume is an integral over all possible random students, normalized on the unit sphere, times all, and then you have then times whatever the teacher is, integrate all those students overlapping with the teacher, minus this cosine epsilon term, which represents kind of like the energy. So this is a typical statistical mechanics approach to representing what would be the phase space volume. And there are many papers on this. And typically, and you might know I have a paper on this. So we wrote a review paper on it. And typically what you do to solve this problem is you assume the teacher is student random, and then what you do is you say, well, I have this data. I'm going to treat the data of the problem as a random Gaussian field. And I'm going to embed my neural network, my persuasion, in this Gaussian field. And I'm going to use some statistical physics. I'm going to take a Hubbard-Stratigraphic transformation. I'm going to do typical Southbound approximation. And I'm going to get what is called a mean field theory, a non-variational mean field theory. And you compute what is basically the error as a function of the load, assuming something like the j's are discrete. And so what you get is a function, which is you get this function of the error, and you get, when statistical mechanics are interested in things like phase diagrams and how many patterns, how much data do you need for the network, and so you get some plots that sort of look like this. And the idea is that the load is like, I know the number of parameters, and I have some number, I'm going to train the model with so many examples. The number of examples, the number of parameters is the load. If I have lots and lots of examples, I do very well. And my generalization error is very small. This is the error, it's the load. And if I all of a sudden don't have enough examples, bam, my error got spikes. And this is the standard approach to statistical mechanics, and we have a review article. And the idea is that basically, if you don't add enough data to your neural network, it doesn't generalize well. You need lots of data. And there are lots and lots of toy models which describe this, and we have a paper on this, which we go through in gross detail, all the various phase diagrams. This is not what I'm going to do. Instead, what I'm going to do is I'm going to say, let's treat the matrices, let's treat the J's in the student-teacher model as matrices. And let's actually take them from a real neural network. And let's say the teacher is not random. We're going to make the teacher be the neural network we're looking at, VGG19, Inception, ResNet 152, something like that. And I'm going to compute the total error. So to compute the total error, I don't want the error as a function of the load. I just want some rough expression for the total error. So I'm going to transform what was a microcanonical ensemble into canonical ensemble. I get something like an integral over all possible random matrices times the exponential of beta trace JT, where this is some matrix overlap between the two random matrices where T is the teacher and J is the student, and I'm going to say, give me my neural network, I know its layer matrix, tell me all possible students students that could overlap with the teacher, compute this interval. Then, by the way, this is the first time I've ever told anybody this, other than my blog. This is all new stuff that we're trying to sketch out. So this is sort of in preparation. And the idea is that instead of using random matrices, we use real data. Well, how do we characterize data? Well, it's either, so we know how to characterize it. We look at the spectral density. So it turns out that this is something called an HCI's integral matrix integral, random matrix integral. And it turns out there's a solution that you can pull out of a paper by Tanaka. And the idea is that if we reformulate this in terms of the expected value over all, I'm going to call A now J dagger J. So A is now, forget the A we talked about an hour ago. A is now the correlation matrix of the students. And I'm going to integrate over all possible correlation matrices given the teacher weight matrices. And I'm going to compute this exponential. And I'm going to assume beta is 1 because I don't know the scale. So like all machine learning guys, I'll just assume beta is 1 and ignore it for now. But basically, that's like the scale of the weight matrix. So beta is like a temperature, but essentially, it's not going to factor in. I'm going to take this. It turns out you can write this a simple expression, which is basically a sum over these generating functionals for the students, or Green functions, times the eigenvalues for the teacher. So all you need to do to compute the generalization error in this sort of theory we'll work out is all you need to know is the eigenvalues of the teacher, which we know because we measure them. And we need to know this generating function for the student. Well, what is that thing? Well, it turns out, I'll skip some of this. It turns out that this is basically an integral over something called an R transform, which is like a cumulative generating function. And it sort of looks like this, and the idea is if you know the R of the student, you can write down the expression for the error. Well, I don't want to keep you guys here until 11, until 7 o'clock. I have some slides where I discuss sort of heuristically what these things are from physics. But essentially what you have is this, you have a simple form of R. When R is Gaussian random, R is Z is just Z. When you have matrices where the students are very heavy-tailed Lagrangian matrices, R takes a slightly different form of alpha to the -1, where alpha is this empirical parameter that we fit. And so it turns out you can write down a simple form for the error. When it's Gaussian, you take R of Z, you plug this through, you basically get something like the trace of the student matrix. So if you were to say if I knew the students from Gaussian random matrices, then you would get this expression for the generalization error for each layer, which looks something like the log of the Frobenius norm squared, or something like that, or log of the Frobenius norm with A squared. And it turns out that when you're very heavy-tailed, which is kind of like our theory, that alphas are actually smaller than ours, but if you sort of close your eyes and use this, and you work out an expression, you get something very similar for the total generalization error. You get 1 over alpha times trace of A to the alpha. So now I have an expression which is kind of like you were asking about this expression for the size of the matrix. And it's quite possible that Mark worked this all out, and this is totally, he knows all this. I have no idea. But basically,
it's none of these kind of calculations. His thing is, it's in a machine learning context.
Oh yeah, I have no idea what it is. But it might be equivalent, right? Like I think that this result, there's this thing called, it's this infinitely wide deep neural network. And I think that this result might be theoretically the same, because when we take the limit, we actually don't take a statistical physics limit. We take this limit, when we do the Tanaka result, we take the limit as n goes to infinity, but this is not actually the thermodynamic limit. It's more like the VC limit, because we fix n and let n go large. So I think that might be similar to these infinitely wide neural networks. So I think that this result could be degenerate. This could be the same as, I'm not sure. Michael thinks that's the case. I haven't looked at the details. So if you take this result and you just do what Michael calls the physics level of rigor, meaning I sort of close one eye and make a few approximations, you can go from here to here. And you basically say, look, I take the trace of alpha sort of like the trace of the trace of A to the alpha, so I can work the cross terms. The trace of a very heavy-tailed matrix, if A and alpha is very small, then the trace of A is basically the sum of the eigenvalues, which is basically the first eigenvalue. So if alpha is like 1.5 or so, or 1, that's going to be very close to true. And so then I get the expression for the total error, or the total phase space volume is basically lambda max to the alpha, and then I just take the log. And I recover that result. which is this alpha log lambda max that we were using as our metric. And that's sort of my sketch of what is a sketch of a theory of where this comes from. And the idea is that basically it boils down to this idea that you're which one should I come up with this one? This idea that in order to compute the error, that there's this physical notion that given a weight matrix for a teacher, I want to find all the possible students that could look like the teacher. So I have to make some guess. What might the students look like? Well, let's assume that they're random, but their correlation matrix has the same exponent as the teacher. So that's my assumption. Let's assume that in order to compute the generalization error, I would assume that all the possible students have the same correlation structure as the teacher, and then I can get out a very simple result, which appears to work empirically very well. And then I can make some other claims about what the energy landscape looks like, but I'm not going to. That'll take another hour to go through the spin glass theory. This is where we are, and I appreciate you guys. I really appreciate the questions, because this is sort of our first real pass at. This last part is really the first real pass at explaining the theory, and I'll leave you with this. If you want to try and install the tool, we're basically, the idea is I want to make a tool that's useful, an engineering tool that people can use to do things, and we're trying to just do different things with it and provide some theoretical basis for why it might work. And, okay, I took 10 extra minutes, I hope that was okay.
This is one of Dave Donahoo's favorite words.
Well, I nailed it then. All right. Well, thanks. I really appreciate it. Thanks for coming.
Thank you.
Can I ask one question?
Yeah.
There's one here.
Some time ago, you displayed an overlay of what I think were all of the alpha values for a large number of
This one?
yeah. A large number of neural networks.
Yes.
And you made a statement that as a physicist, you would expect to see a spike around 2.
Yes.
But you didn't explain the physical background for that.
Okay, I'll explain. Last time I was here, I got hammered on that. So I used to work with a guy at BlackRock who's advisor of a guy named Peter. He spent a lot of time trying to predict earthquakes and market crashes, and there was a theory that we had that these are critical systems. They're systems near a critical point. They're sort of, and systems near a critical point in theoretical physics all have the same critical exponent. So the critical exponent is a powerful exponent, so they would all have the same exponent. And of course, these are infinite systems, right? So when you do theoretical physics, you talk about critical phenomena, phase diagrams, you talk about infinite systems. So Dieter's and my friend Matt had these notions that if you were to apply, this comes from our renormalization group theory. And so if you were to apply this to finite systems, what you expect is when you fit many phenomena, you find that there are many phenomena can fit a power law. And when there's an underlying mechanism that drives the critical dynamics, you expect the power law exponents to be very similar empirically. And in the infinite limit, you expect them all to be the same. So in our case, what I'm saying is that I'm sort of using that idea that I sort of have this qualitative idea that neural networks behave like a physical system near a critical point. So like a water in between where it's liquid and boiling. It's like a sort of right at that area where it's just about ready to
When
boil.
you say the neural network behaves like this, are you talking about a single network, or are you talking more about the process of training and going into overtraining?
The process of training it when it becomes well trained.
And then
That the weight it behaves as if the stability point of the optimization problem behaves like it's a critical point.
Now I'm with.
Or way more practically, I would even say it behaves like I even have a more wild conjecture. I think it behaves like a finite state attractor. I think that these are finite sized systems, and I think that there's finite state attractors, and if you study them in the infinite limit, you get different behavior than in finite size. And I think that finite sized attractor is similar to what is a critical point, which is a steady state solution of the normalization group equations. But that's a bunch of hoo-ha. It's a bunch of jargon, right? The idea is that this thing is sort of on the border between
Something
stable and unstable.
phase change.
Right, and if you think about in the physics, the theoretical physics notion,
Your other diagrams are phase.
yeah, you're here.
Those are phase.
You're here.
Yeah.
This is the critical point. You're at this sort of triple point, or you're somewhere on the phase line. And there are some people who think that neural networks is a theory. So the idea of the phase line, and there's actually guys in, we have a whole other talk, we talk about like actual neurons. And if you look at the critical dynamics, the neuron dynamics, they also display power law behavior. And so there's a whole group of guys who do sort of theoretical neuroscience, and they believe that the brain operates like a system near a critical point. And when they measure the neural dynamics, they see something called self-organized criticality. So they see these power law exponents, and they all seem uniform. That's sort of where the idea comes from.
What's SG?
The spin glass. That's that funny.
I got it.
Yeah, that's
Interesting.
So anyway, that's so that's why when I saw this, it's like wow, it's like this is something very interesting. It's you're seeing all the exponents seem to concentrate around 2, which tells me that when you start looking at some of these models, then the good models should have small. They shouldn't be too small. If they're below 2, I actually think they may be able to drink. But my estimator is not that good, and I'm doing something goofy. I'm also some of these I'm estimating small matrices. You know, like 64 eigenvalues. So if the thing gives me 1.5 and I say it should be 2, nah, it's probably 2. You know, one get the estimate, you only have it's not that great. These are estimates. So that's why I like to look in the aggregate over, so I can wash out some of the error.
Thank you.
No, you're welcome. Yes.
Do you do some type of pre-processing to the spectrum before estimating the alpha? Because
No.
there's a set of spikes that might make the estimate incorrect.
We don't see them. You only have finite data, right? So you have 64 eigenvalues. What's spikes and what's not? So we fit the alpha, and we fit the Marcenko Pastur distribution, and then you can select which model you like best. So we do this. Is this Marcenko Pastur or is it power law? That doesn't let that. I would say that's power law. You'll probably get a pretty good fit. Is it a great fit? Man, sometimes it's a really good fit, sometimes it's not. Can you use it? Maybe. We try to use it, right? It may not be great, but we try to use it. But that's what we can do is we can actually do a Marcenko Pastur fit, and we'll actually count the number of spikes. And remember I gave that NP soft rank metric? That's what that is. It counts the number of spikes beyond the bulk region. So we have a metric for that as well.
Charles, is this mostly physics intuition, or does chemistry come into it too?
Well, I did chemical physics, so it's a little bit of both. I do theoretical physics, but I'm not trying. The difference is that a lot of people who do statistical mechanics, they build a simple model, and then they try to make inferences of that model, and they try to project the deep learning models onto the models they know. God, I don't want to do that. I want to figure out what's really going on. So I want to build a model that represents the data, as opposed to a simple model and sort of squeezing the data to make it fit the model. And I think people who like Gaussian random matrix theory or Gaussian spin glasses, they're taking a model they know how to solve and they're projecting the data onto it, which they're forcing the data into the model as opposed to the opposite. To do engineering, you need to look at actual data and make the model work for your data.
Regarding your derivation for DN,
yes.
Was the derivation, you said the derivation was for a multi-layer perceptron, or is it a single layer perceptron?
This is for, what I do is I assume all the layers are statistically dependent, and I compute the error for each layer. So I'm not looking at cross correlation between layers. So this is just this derivation on this stuff. This is just to give me this equation, the alpha log lambda max, which is basically alpha and lambda max they characterize the truncated power law.
But that's for a single layer.
For a single layer.
Yeah, so my question is there any reason to believe these sums over the different layers?
Well, as I said, I did the simplest thing I can do because I'm very lazy and I'm self-funding. But no, I just assumed, right? I'm just going to make this assumption that the layers are statistically independent, and I'm going to try it. And if it works, I'll use it, and I'll go back and try to fix it. You know, we want to try to go back and fix it, and maybe we can fix that up. What I would say is I think the dominant effect is the individual layers. There are models like path norm, for example, which look at the path, they're like path norm models. So we don't quite know how to do that yet. But we're going to work on it, that'd be great. But no, I just am very firm, right? Let's just assume that's true, and that'll get me to a certain point. And if I can get all the way, then I'll go back and try to fix. I'm amazed I got this far. I mean, I'm actually quite astounded by, this astounded me, that it works so well. That you get such good results when we're doing something which is so naive. You know, this is not, you know, there's no particular reason why. I mean, I sort of asked like this why this might work. It's, but it seems to work pretty well given that it's fairly crude approximations.
Okay, well.
Okay.